Now that you've worked through the notes on stress and strain, it's time to attempt our first tutorial on the work. So having a look over here at the very first problem, number 1, which is a very simple stress calculation, but nevertheless we need to go through it and make sure everybody understands exactly what to do. And in this first one, it talks of a short cast iron column, and they give you an external diameter and an internal diameter. So it sounds like a round object, a column that is hollow inside. We'll show you a sketch in a moment. Now this column is said to support an axial compressive load of 12 kilonewtons. That would be 12,000 newtons. We've got to find the stress in that column, and an answer is given. So here's a sketch of what it probably looks like. So the column is circular, it's round on the outside, it is hollow on the inside, there's nothing inside there, just air obviously. So the material is then in what would be known as an annular shape. So if you were to take a cross section through this column and draw it here alongside, you would have an outer circle, we'll call that diameter D, or have diameter D, and inside diameter of lowercase d. Now the area of an annulus is the area of the outer circle minus the inner circle. So pi over 4 would be common to those. So the convenient way to write down the formula for an area of an annulus is pi upon 4, and then in brackets capital D squared minus little d squared. And then back to what you learnt in the notes, stress or intensity of stress is simply the load applied over the area that is resisting that stress. Now we like to use base SI units. You'll see there that the load goes in as 12 kilonewtons, which would be 12 times 10 to the 3 newtons. And beneath it is the area, pi over 4, and here are the two diameters. Now remember, 0.04 is the 40 millimeters expressed in meters. We only work in the base SI unit of dimension, which is meters, and we subtract from that the inner diameter. Remember, the outer diameter was 40, so from here to here was 40 millimeters, and then on the inside from here to here was 30 millimeters. Now you put that all in your calculator and you press equals, and you'll get an answer with a bunch of zeros. Now remember to use your ENG button and then step through until you get the answer in a presentable form. In our case, 21,83 megapascals. In other words, 21,83 times 10 to the 6 pascals would be the way you'd like to get that answer expressed. So there's the first one done. Let's take a look at the second one. Here you'll see they talk of 3 steel bars, all of the same length and diameter, and they are evenly spaced, and they support a mass of 4 tons in tension. Now remember, a ton in the metric system is 1,000 kilograms, so we're talking about 4,000 kilograms of mass that is being supported. We must find the stress in these bars, and they say the diameters are 25 millimeters. Now the diameters suggest that the bars are indeed round. So let's take a look at that solution. If we look from the side, this cross-hatched set of lines here would indicate the support structure, perhaps the roof of the factory or wherever it's supported from. Then these are depicting the 3 round bars, which are vertical, and somehow we have this mass of 4 tons attached to all of that. And finally, we're going to have to assume that the 3 equally support their share of the 4 tons. So if we take a cross section through any of the bars, it would be round, and the area of a circle, a circular shape, is pi over 4d squared. And back to our same old stress formula, stress is load over area. Now if you're supporting 4,000 kilograms, the force required to do that close to the earth, you would have to multiply, as we know, mass by g to get that force. So 4,000 times 9.81 would be the force involved, and beneath it we've got the area of the circle, pi over 4 d squared. Remember that the diameter goes in as meters. 25 millimeters expressed as meters is 0.025, and don't forget the 3, because there are 3 of these bars. In it goes to your calculator, and 26.65 megapascals is the answer. Time for number 3. Number 3 speaks of a lap joint, and a lap joint is basically as we see over here, two plates that are placed one on top of the other for a short portion anyway. And then in our case, we're going to drill 4 holes right the way through both plates. So you can't see the holes in the rear plate, but they go all the way through. And then a rivet is inserted in each of the holes and it protrudes out the other side. And then they would beat the end of that rivet over, hence holding these two plates together. Now if you look back at your notes and you look at single shear and double shear, this is clearly a case of single shear, because only on the surface where these two plates touch will there be a shearing action of the rivets. So the calculation is as before. Stress is load over area. They spoke of 12 kilonewtons of tension, which is obviously shared between each of the rivets. So here we have our 12 kilonewtons or 12,000 newtons. And the area is, once again, the area of a circle, pi over 4, d squared, d being 10 millimeters expressed as meters. And there are 4 rivets, all taking their fair share of the load. And the answer comes out to 38.2 megapascal. On to number 4. Here we have a tank, mass 313 tons. Remember, each ton is 1,000 kilograms, supported by 4 pipes. Now, perhaps those pipes are feeding liquid to that tank, we're not sure, but it sounds like these 4 pipes are in fact supporting this tank. Now, each pipe has an external diameter of 200 millimeters, but we don't know the internal diameter. The stress, however, in the pipes is not allowed to exceed 68 megapascals. Now remember, if you make the internal diameter smaller, you'll in fact drop the stress, because there'll be more material to support the weight. So let's go to the sketch. Right, here's the sketch. We have, very much like the previous ones, 4 of these pipes, which are obviously hollow inside, circular outside, as we've done before. So the cross section would be 4 annular areas, and the full mass being supported is 313 tons, or 313,000 kilograms. So here's our normal formula as we've done so many times before. Stress is load over area. The load would of course be the mass times the gravitational acceleration at the Earth, which would give us the full force being supported in those 4. And the area is 4 areas, each one being pi over 4, 0.2 squared, that's the outer diameter, the 200 millimeters converted to meters. And here's the unknown, the d squared, the little diameter inside, that is from this dotted line to that dotted line. And of course all of that may only equal 68 megapascals. So in this case, just in case you're battling with your calculator inputs, I've put down every step the way I do it in my calculator. Normally I wouldn't present all of this, but let's just go through it quickly. What I've done is I've just manipulated the formula so that I get the unknown on the right hand side, and to do that I moved the 68 times 10 to the 6 across the equal sign, so it went below, and conversely I moved this 4 times pi over 4, this area part over here, I moved it across the equal sign so it went above the line. And I did the same by moving the 4 times pi over 4 across to beneath the line as I cross the equal sign. And my goal is to try and get d on its own on the right hand side, which I've achieved by moving the 0.2 squared across the equal sign, changing the sign. And now we have a negative value on both sides. We can multiply both sides by -1 and convert them to positives. We're left with d squared equal to a number. We take the square root of that number, and there we go, and we have d at 0.16 meters. Hopefully that helped a bit for those battling with their calculators. Now we get on to number 5, and in this one we deal with what's known as a bell crank. Now a bell crank is a handy device for changing the direction of a force. And in this case, the force, let's say, is applied in a direction straight upwards. And perhaps in our machine, we wish to have the force in another direction, in this case, horizontal from vertical. So we're going to apply a force in a vertical direction. And via this bell crank, we are going to get out a force which we could then use elsewhere in our mechanism in another direction. At the same time, we can also, by means of leverage, change the magnitude of that force by having varying lengths over here. Now, where would you use a bell crank? Well, here's one example. There obviously are many. Here's an aircraft where in the wing we wish to operate the aileron, which is this control surface over here, and the force comes from the joystick in the cockpit. Now, the joystick is connected to a push rod which goes all the way down the wing here, and you can't see it, but underneath the wing is a little hollow, and in there is a bell crank exactly like the one we have in this problem, which changes the force from the pilot, which is aligned with the wing, to a force in this direction, which operates a short horn under the aileron and makes the aileron go up and go down to control this aircraft. So that's one example. So if we look at the actual forces, they tell us that the applied force is P, which is unknown. Let's just read the question once more. It says, the bracket shown is in equilibrium under the action of the forces acting on it. We must find the force P for a start, so let's do that. If the force over here is 2 kilonewtons, and this bell crank is indeed in equilibrium, we can take moments about a convenient point. In this case, I'm going to use the pivot, which is where the pin is. And if we look at the situation, we've got the sum of moments about the pin adding up to 0. In other words, clockwise moments are equal to anti-clockwise moments. Clockwise moments, I can clearly see P multiplied by 0.15. There's P. It has a moment arm of 0.15 back to the pin, and it's equal to the only other moment, which is an anti-clockwise one, which is 2000, clearly trying to rotate the bracket anti-clockwise about the pivot point. So 2000 is the magnitude of the force, 0.09 is the length of this lever arm. So for equilibrium, it means that P must indeed be 1200 newtons of force. You'll see that 1200 is less than 2000, and that makes sense because this is the long arm of the bell crank and this is the short arm of the bell crank. Right, now if we look further into the equilibrium situation, this whole bell crank is standing still in space under the influence of the forces acting on it, and there are 3 forces acting on it. It feels a force upwards of 1200 newtons, it feels a force rightwards of 2000 newtons, and there must be a force here at the pin keeping it where it is. That's the third force. So if we sum these forces, draw them as vectors, 1200 plus 2000 would take us way out here, and it stands to reason that to keep the lever in equilibrium there must be a force coming from somewhere, in this case the reaction force of the pin, keeping the lever in equilibrium. So by Pythagoras we can then analyze that 1200 plus 2000 summed via this vector diagram would mean that this closing vector over here, from here to here, is the support reaction. And using Pythagoras, you can see it comes out to 2332. And finally, that force is the one felt by the pin over here, which is keeping the bell crank in equilibrium. And they also speak of double shear. Now the double shear is probably because there's a plate on either side of the bell crank, meaning there is shear above the bell crank and shear below the bell crank, 2 shear planes. So here's the 2 for those doubling up of the areas. So there's our force over the area resisting the shearing force, which is 2 circular areas of pi over 4, 0.006 squared. The 0.006 is the 6 millimeters expressed in meters. So the shearing action, or the shear stress in the pin, is 41.24 megapascals. Now in number 6 we look at a knuckle joint. Now a knuckle joint is one that's depicted over here. We have 2 rods which would be most likely in tension, and there's a connection. So somewhere in the structure we need to be able to disconnect these rods, and to do that we have one part fitting inside another part. We could call this a yoke. And passing through the whole lot is a pin, in our case diameter 16. So we have tension, force P, and we're going to set up, as we know by now, double shear along these 2 shear planes over here of the 16 millimeter pin. But what's interesting about this problem is it's a typical design problem where we have to look at more than just one aspect. And here are the 2 aspects. we are given allowable shear stresses that differ in the two materials, that of the pin and that of the rod. So to do this, what you do is you consider one aspect at a time. So here's a heading. It says consider the direct stress in the rod, and that's here and here. Now we know by now that stress is load over area, so load is stress times area. So what load could we possibly have in the rod if we are not to exceed 120 megapascals? Bearing in mind that the cross-sectional area of the rod, being circular, is pi over 4.018 squared. So that solves out to be 30.54 kilonewtons. That's the most force we can have in this rod to set up a stress of 120 megapascals tensile. So that's one part done. Then we move on to the pin, which, as we've already said, is in double shear. There's this one shear plane, there's the other shear plane, and we have tau, which is typically our symbol for shear stress, and we do much the same as the other one, and we get a little formula that says load is shear stress times area, and there is our allowable shear stress, the 80 megapascals shear allowable for the pin. This 2 is of course for the two shear planes. Remember, there's one, there's another one. Pi over 4 d squared, the d being the diameter of the pin. So now we get 32.17 kilonewtons. We sit back and we look at it and we see 30.54 and 32.17. So which one must we choose for our design? Well, if you just grab the bigger one, you're going to be wrong, because if you were to subject this knuckle joint to 32.17 kilonewtons, you would exceed this shear stress over here. So in this case, you have to take the lesser of the two and set that as the maximum load that the knuckle joint can accept, thereby not exceeding either of the two allowable stresses. Number 7 is very similar to numbers 2 and 4, which we've done previously, except that in this case you'll see we have steel rods, 2 of them, supporting not only the 1,000 kilogram mass there, but via another 2 rods, which are of a different material, brass, there's a further mass supported down here. So to start this design, let's consider the steel rods first and look at stress being load over area in them, or in other words, load is stress times area. Now the 2 steel rods, there they are, support not only the 1,000 kilogram but also the mass M. So 1,000 plus M is the total mass that they support. We're obviously neglecting their own mass because that wasn't given in the question. But anyway, they're supporting 1,000 kilograms plus the unknown mass M. We multiply all of that by 9.81 to get a force. And we're only allowed 120 megapascals in those steel rods. There are 2 of them. Each one has that cross-sectional area. So as far as the steel rods go, we can make mass M 1766.9 kilograms. That's this one down here. So that's half the design done. But we need to satisfy the second design requirement and look at the brass rods. Now the brass rods, being the last ones down here, only support the mass M. So mass M times 9.81 is equal to their allowable tensile direct stress. There are 2 rods, that's their cross-sectional area. So as far as the brass rods go, 819.8 kilograms is as much as we can make mass M. So in a very similar fashion to the last one, you can't just take the bigger number. You need to look at the design and decide what is going to result in the most conservative design and meet both design requirements. And that would be selecting the lesser of this number and this number and setting that as your answer. 819.8 kilograms is the most mass that M can have. And that's the end of this tutorial.